Okay, so I'm going to talk about the heap sort algorithm, really very classic algorithm. And heap sort kind of goes what we call, I'm going to talk a little bit about what are called priority queues. A lot of the videos like online, I noticed on YouTube talk about maximum heaps, and that's what we're going to talk about. So it takes a minute for it to open up. And just stop me at any time you have a concern or a question. Just call out. You don't have to raise your hand or anything. Because I probably won't see it. Okay. So first of all, let's just talk about what we're we're going to talk about priority queues for one. So a heap is an example of what's called a priority queue. And so a queue is, we didn't really talk too much about queues. I did talk about linked list, which is like a chain of nodes, and every node tells you, has some data and tells you where the next node is. So queue is just kind of a special type of linked list where you add at the end and remove at the beginning. So it's just like a line, like, hopefully if we're polite, we stay, if like you're going to movies, it's first in, first out, and the person at the front of the line buys their tickets and then is deleted from the line, and a new person comes along. Hopefully they, they're polite, they go to the end. So that's basically what a queue is. And then there's something called a priority queue, which you'll learn about probably more if you take an operating systems course. And so when we, like, the computer has like a queue of, it's also fast. You never know, you don't really know that they're queued up, but there's all these kind of tasks that the operating system has to take care of, and they kind of line up. But then there's some tasks that are more important than others, so they can jump ahead in the queue. So like saving a file, opening a file, running a program. But what would be important? Let's say maybe it looks like there's a hardware failure. Maybe like saving a file before our computer dies. That might then you'll jump the line. Okay, so that's what this kind of heap. So this heap is. It's an example of a priority queue where things are ranked in terms of their importance. And so let's just. But we're mostly going to learn about how to create heaps, maximum heaps, and how to delete a value from a maximum heap. Okay, so some of this is writing I did in the last hour. Okay, so it doesn't matter. Okay, so there is and I can put the code online, but really mostly what we're going to do is just be doing a bunch of drawings. And so we're going to visualize these heaps in terms of drawings, and then I'm going to talk about the code a little bit. And there's two types of max. There's two ways we're going to create what's called a max heap, and one is where it's this one where it corresponds to this. We're going to add the keys. We create this empty heap and then add keys to it one by one. And the other one is where we actually pass a bunch of keys to this heap program and then create what's called the max heap. So I haven't really talked about what a max heap is yet. So a key is just like think of it as like an integer. In this case, it's just a way of ordering a bunch of nodes. Okay, so like we can use like characters like A through Z, or integers. So there's we can actually use any class that implements comparable. But for us, we're just going to assign a priority either with a letter in the alphabet or with a number. And so there's some of these methods that we're going to we would talk about, like how to insert a key into a max heap, how to retrieve the largest key, and how to delete the largest key. We'll talk a little bit about that. And also we want to be able to get the size of the heap. So what we're going to do, we're going to create these trees. And here's just an example right down here. So let's see if I can. And all these diagrams I swiped from the Sedgwick website. I didn't make this beautiful diagram right here. So I don't know if you can make it a little bit bigger. So basically, this is what our goal is in the class, learning how to draw these trees. And so we're going to do a lot of tree drawing in this unit. And so one thing you notice about this tree right here is that every node, first of all, has two children, and the data stored in each node, like this T, and the left child is S, and the right child has an R. Doesn't look like an R to me. You'll notice that the data stored in the parent is larger than the data, or larger than or equal to the data stored in the children. It can be equal. And the other thing to notice is that, we'll talk more about this later on. we fill in these levels left to right. So like T is at level 0. And then the next level, which has the S and the R, that's level 1. And they double, right? So the first level 0 has 1 node, basically 2 to the level number. So level 1 has 2 nodes. Now level 2 has 4 nodes, that P, N, O, and A. And now that very last level, it's incomplete. But if we were going to add a new node, we fill it in from left to right. We just don't arbitrarily put it in anywhere. Now, when we talk about searching, we're going to have trees where we do put things in arbitrarily. But for right now, we're going to insert key data from left to right, and these nodes from left to right. So the next one would be this left child. If we're going to insert another node, it'd be the left child of O, and then the right child of O, and then the left child of A, and the right child of A. So we fill the level from left to right. So this level 3 would have 8 nodes, and if the level 4 would have 16 nodes, it just doubles every level. So, and so basically, yeah, this is the key thing here, though. If the key in every node is larger than or equal to the key in that node's children, and that's what we have here. If you look here, every node, like R is greater than O and A, T is greater than S and R, like N is greater than H and G, and P is greater than E and I. And S is greater than P, and S is greater than N. So if S is greater than P, look, P is greater than E and I, S is greater than P, so S has to be greater than E and I. So, okay, so let's move on. So the goal is if we were given a bunch of keys, if we're given a bunch of nodes and has this like these keys, storing these keys, how do we kind of rearrange it so it has this heap data structure? Okay, so one thing is first of all, how does the computer actually, we see this. So this is what we're going to see. Maybe I just erase this, mostly because it's kind of like magic, right? Okay, so we see this. This is what we're going to see. This is how we're going to visualize what's called the max heap, where the data in each parent is greater or equal to the data in the children. But how does the computer actually store it? So for our code, it's actually going to see what's the very top node. It's T. Look at it, it's TSR, and then so this is this T goes at position 1. And the S is at 2. So we're just going to go level by level. The R is at 3, the P is at 4, and so forth, and the N is at 5. And we just go on and on and on. So there's how many nodes are there? There's with 11. Right. So this G here would have to be at position 11. And so we're actually not going to use position 0. So we have this array which was called so in Sedgwick, if you look online, he just calls it PQ. So you're actually going to store these keys in an array. Where the parent, what's at position 1, that's the parent, that's at position 1. And the children of I are located at indices 2 times I and 2 times I plus 1. So this is always the left. The left child is always at 2 times I, and the right is always at position 2I plus 1. So you see here, like T is at position 1, the index is 1. You multiply 1 times 2, and you get 2. So that S has to be the left child of T, because it's at position 2 times 1. And this R is at 2 times 1 plus 1, or 3. So R has to be the right child of T. So that's what we see right here. Right? S is the left child of T. R is the right child. So look, what's the left and right child of R? So that's O and A. So R is at position 3. Right? The R is at index 3. So the left child has to be at position 2 times 3, which is 6. And the A has to be at 2 times 3 plus 1. So that would be 7. So if R is stored at position 3, its children have to be stored at position 6 and 7 in the array. And that's what we see right here. And it's pretty easy to fill in, just by looking at this array, it's pretty easy to recreate the tree. You just start the T, you go from left to right. You start the T at position 1, and just go, S and R, and you just fill it in level by level. And then the next 4 are P and OA. So P, N, and so forth. And there's actually going to be 11. There's going to be 11 of these nodes. And so why do we not use position 0? So what's 2 times 0? It's 0, right? So this wouldn't work. So like the left child of position 1 is at 2 times 1, or like the left child of, so like O is at, what do we say? The R is at position 3, and so it's left child. These are that's the left child of R, and that's the right child of R. Okay, so this is, so I multiply 3 times 2, I get 6. I multiply that 3 times 2 and add 1, I get 7. But 2 times 0 is 0. Yeah, so if you multiply index 0 by 2, you're going to stay at 0. So this wouldn't work. So that's why we kind of skip this. Now there's this Sedgwick, no, not this Sedgwick. I did use a Zybook last semester on this material, and in that author, those authors did use position 0, but they use a different scheme. So the left child would be at 2i plus 1, and the left child would be at position 2i plus 1, and the right child would be position 2i plus 2. But I think this is more elegant. So we're just going to use this. We're going to skip position 0. The left child of any node is at position 2 times I, and the right child is at position 2 times I plus 1. So if the parent is at index I, the children are at 2i and 2i plus 1.
I have a question.
Yeah, go ahead.
So, how come you didn't go through 8 through 11?
Oh, I was just not gonna.
Okay.
I was just.
But during the exam, you do the full thing, right?
Yeah. I see what I was doing here. I was just showing if this is the array, how can we recreate the tree? And I said, yeah. So you just go. Yeah. So then the last, I went up to A. So then now you just go to the next level: E, I, H, and G. But I was just trying to show it's pretty. If you have the array, it's easy to go from the array to the tree. You just go level by level. Does that answer your question, or I just stopped because I figured,
Oh, okay. Yeah. Yes, sir. Thank you.
Okay. So, and then also it's easy to go from the tree to the array. You just start at position 1, right? So that the top is position 1, right? And the next level is 2 and 3. So it's easy to go back and forth between the array and the tree. Okay. So now, but the computer is working with the array. It doesn't know about, the computer is not drawing pictures like we are. But any other question before we continue? Okay. So there's a couple of things we're going to do. We're going to do exchanges, just like we exchange in quicksort and merge sort. So we're actually going to swap values or exchange values in this integer array. And so one thing is, again, we have our friend, the less method. And this is true. So this is true. So let me see if I can write this. So it's going to say the elements in P sub Q, the objects stored in P sub Q implement comparable. So it has that compare to method. So it's true when P sub Q of I is less than P sub Q of J. Right. So, but it has to, the data stored in this PQ array is really an array of objects, and each object implements compare to. So when you compare objects, you have to use the compare to method. So if PQ of I compared to PQ of J is negative, it returns a negative value. That means the calling object is smaller than the input object. Okay, so that's one method. We're not going to have to use the code. You can easily just, if once you know the algorithm, all you'd have to, you'll see. We're just going to look at the tree to actually do this. And then we have the exchange method where we just exchange the data stored in position I and J. But the computer is actually going to use all this, it's actually going to compare objects, and it's going to use the compare to method to compare objects. Okay, so n is equal to, so remember this that uppercase n, that's equal to the number of elements in the heap, in the tree. Okay, so the array, this PQ array that I showed you, it might be large, it's probably larger than n, right? So it's got some extra space. So like right now there's that heap I showed you, it has 11 values, or like 11, but there's really more out here. And so there's some extra space, just so as we add more keys, we'll have a place to put them. Just like, you go into a movie theater or something, there's lots of extra chairs. I mean, they don't bring a chair every time someone walks into the theater. There's all these chairs ahead of time, just like a classroom. Unless the classroom's overfilled, but but that's kind of typically the way it's done. So the same thing with kind of analogy with the array. So there's a lot of space. This array is probably much bigger than n, but I'm saying so, but it's only positions 0 through, it's only the data that's in positions 1 through n that are considered part of the heap. And it's going to kind of become important later on. So there might be elements in the array that are actually not considered part of the heap, right? So it's just positions 1 through n that are considered part of the heap. So for this problem, because there's 11 nodes, n is equal to 11. So if we decrease n, the data, let's say I said, oh, n is just 10 now, you would still have this data at position 11. It just wouldn't be considered part of the heap. So, okay, so let's see here. So we have the exchange. Okay, so let's say we're going to learn 2 algorithms for creating a heap. And then we're going to learn how to use this kind of heap data structure to sort. You're only going to do one step because it takes too long to go through the whole thing. This first version, this first algorithm is just going to add keys 1 by 1. So every time you add a new key, you increase n by 1. Okay, so you're going to put the new key at position I, and then you're going to increase n by 1. The maximum key is always at position 1. Yeah, again, this is just kind of reviewing some facts. Position 0 is just empty, right? So n denotes the number of elements in the heap. So when you add a new key, you put it at position n plus 1 in the array and increase n by 1. So, and I keep getting these text messages. Okay, so I'm just going to show you this code here. You don't actually have to remember this code to do the algorithm, but basically what we're going to do is what's called swimming. Okay, so you're going to add a new key, and the thing is, when you add a new key, you want to make sure that your parent is greater than the new key. So you want to make sure. So let's say we have something like this. Let's say we have C, and then we have A. Okay, so there n is 2. And let's say, okay, let's add a D to it. So you add it up always at the first open space, and so you add it at position 3. 3 would be the right child of C. So let's say we're going to add a D to it. So now n is equal to 3. Okay, but look here. The thing that we will insist on in this tree is that the data stored in the parent is greater than or equal to the data stored in the children. See, C is less than D. So we violated that property, but what we're going to do is use this method right here. Because that's what happened. When you add a key, you add it to position 3 in the array, and then you actually call this swim. And so what you'd be doing is we put k equal to, we call swim 3, because this is position 3. And so what you do, so first of all, is k greater than 1, because the C is at position 1. So if you're position 1, you can't look at your parent. See, what this method does, it looks at the parent and see, is the parent smaller? If so, you do an exchange. So while k is greater than 1, because the node at position 1 doesn't have a parent, and then you say less k over 2 comma k. So remember, the children are at positions, see, k over, so the parent of k is at position k over 2. So remember, the children are at 2 times I, and 2i plus 1. Sorry, my printing is terrible. And what happens when you divide 2i? 2i divided by 2 is just I, and 2i plus 1 divided by 2 in Java world is also I. So when so basically you divide any index by 2, you have the index of the parent. So basically, this is saying less. So it's saying, is the value stored at k over 2 less than the value stored at k? So like for our case, if k is 3, you'd be saying is less 1 comma 3 true. In our case, that's true. C is less than D. So in which case you exchange the value at k with its parent. So in our case, we'd call the swim method, we check its parent, and we would put the D up here and the C down here. And that's all it is. You're just looking upward at your parent. And so we're going to actually look at a bigger example, but this is basically this part one. They say there's two algorithms for creating a heap. And the first algorithm all depends really on this method right here. And so I'm just trying to show you some of the code, but when you actually write the problem, you don't even, you might not even be thinking about the code at all. So let's just look at an example right here. Let's see if I can make this a little bit. And again, I swiped these photos from the Sedgwick website. Oh, I'm sorry, I'm going smaller, not bigger. Okay, so let's just look at this swim operation here. And so he actually skips a step here. I'm going to show you what it is. So notice here, students, the P is greater than T. Uh-oh, that's bad. Because remember, we want the parent to be greater than the child. So what happens is so we compare P and T. We see that P less than T is true. So we exchange that P is actually at position 2. So we exchange what's in position 2 and 4. All we're going to do is look at the parent. T looks at its parent P. Oh, T is greater than P, or P is less than T, we exchange. So the first exchange would actually be S, T, and you're going to have the R and the O and the A. The right side will be the same. See, we exchange T and P, so the P now would be the right child of T, and everything else stays the same. All we did was we exchanged these two values. We exchanged P and T, but we're not done, right? You have to keep, so a common error, when I've seen this before, students will do one exchange and then they're done. But notice, before you move on, ask yourself, is this a maximum priority queue? So you check every node and you look at its two children. Is S greater than T and R? But right away, we know that's false. S is not greater than T, right? So so now we have a problem with S and T. So what it is, so first we exchange T with P, and now you have to keep looking up at your parent until you either, the parent is greater than the child, greater than or equal to the child, or you're actually at position 1. So T is greater than S, so there's one more exchange here. See how it exchanges T and S? And also you can see how he's shading. He has that kind of, he moved the P down and he moved the T up. But it was two separate exchanges. So the final answer involved two exchanges. The first is with P and T, and then the second is with T and S. That looks pretty bad. So any question on that? So students, this is actually basically, we're going to go through an example here, like a worksheet problem, but this is basically kind of how you do the first problem on the quiz. So let's actually look at, a complete problem here. What's on the next page? You think I didn't write this? I keep going, what's that? And I did look at it just not that long ago. I just forgot it right. Okay, so how do we insert a new key into a heap? So if you've never learned this before, this is like a big moment in your life, a big moment in your computer science life. So, okay, so first of all, this is really important. We increase n by, remember, n is the number of keys. So remember, we're storing this in an array. So positions 1 through n in the array are considered part of the heap. The array may have more values, but it's only positions 1 through n that are considered part of the heap. And then you place this new key at position PQ of n, and then you perform the swimming operations. So let's just look at an example here. So, okay, so let's just look at this here. So this is the advantage where I'm in the classroom, versus doing this Zoom. So in the classroom, I have this on the screen, then I'd start writing at the board. But let's do part of this, and then I'm going to open a worksheet. We'll do a complete problem. So the first thing, the step 1. So first of all, we're going to put S, O, R, and T into this heap. We're going to create a max heap by inserting S, O, R, and T one by one. So how many keys are there? There's 4. So your answer is going to have 4 trees. The first tree will have 1 node. The second tree will have 2. The third will have 3. And the fourth will have the complete answer. So we'll actually so the first one is just S all by itself. And I'm not going to draw circles around it just to avoid a big mess. And then the second one, okay, so remember we insert keys from left to right. Okay, so the S is here, and now we're going to put the O in. And then you ask yourself, you look up, you compare O and S. Well, S is greater than O, there's nothing to do. We're all set, so that we like that. Now, students, for some reason I remember doing this an hour ago. Isn't that terrible? Okay, so SO, I'm not sure I like this problem. Okay, okay, R, okay, so now you look upward at S, and R is less than S, there's nothing to do. Okay, so far we're fine. Okay, so, but it's 4, okay, so and then plus I have a worksheet problem. Let's look at 4. Again, so now, where do you put this? See, right now, what does the array look like? SOR, 0 is left blank. It's SOR. No, that's 1. Okay, so now we're going to add this. So right now your n is 3. This is before we do the 4th step. Your n is 3. So now we're going to insert t. So insert t, so you increase the n by 1. You insert the t at position 4. The t is there. Okay, so now, so t is the left child of O. So this is, O is at position 2. The left, so position 2 times 2 is 4. So the t is right here. And now what happens is, well, now you look upward at its parent. See, now you violated the max heap property. O is less than t. We want the parent to be less than the child. I'm gonna have to plug my computer in a minute. I want to take a second. Sorry about that. I thought it was plugged in. Oh, what do I do here to stop it? Okay. So then, so you would just write one. Sorry, students. You're gonna write 4 trees. So you write SOR, the T would be here. And what you would do is you keep looking up. Well, you can exchange O and T. But see, we're not done. You have to keep looking up until you can't do any more exchanges. So then you exchange T and S. And you don't have to show all the exchanges. So for every key, there's going to be, there's a tree for every key. So there's 4 trees here, S, the 1, 2, 3, 4. And then, so I showed you all the exchanges just for emphasis, but in the end, the final array would look like T, S, R, O. And the greatest value always has, the one thing you do know, students, in the array, if you're just looking at the array, the largest value has to be at position 1. So if I say, okay, we're going to insert SORT into a max heap, I know that at the end, the T will be at the parent of all parents, and it'll also be at position 1. So unless there's any questions, I thought we could do a little bit of a longer problem.
I got a quick question.
Yeah, go ahead.
I was curious if there's like a minimum priority queue, like pretty much the
Yeah,
opposite.
Absolutely. So you can do everything that we're doing right now. You just change max to min, and then the parent is less than or equal to the 2 children.
Okay.
So instead of, so when you look up, you ask yourself, am I less than my, let's see, you look up, are you less than the parent? If you are, you do an exchange. Does this answer your question, Phil?
Yes,
Yeah, you can actually do that. Absolutely. So, so let's just look at this problem right here. And first of all, so let me just turn my power on. Just take me a second. I apologize about this. I don't want the computer to. Okay, that's better. Yeah. Okay. So it's charging up. Okay. So let's just open, and I have worksheets here, and then I have some old quiz. I found I just was looking on YouTube, and I saw a couple of good videos as well. Pretty much just say what I'm saying. I think but maybe, just another resource if you want. Okay, so let's see here. So let's just, I'm going to do a few steps and then we're going to look at my very nice solution. Okay, so there's actually three, so these are the three, so this problem one is corresponds to what I just talked about. So draw the tree that corresponds to C, DJ, RET, B, DV. And notice we have two Ds in there, and that's fine. So you can have repeats, but just remember when you do an exchange, you only exchange if you're strictly greater than the parent. Okay, so so I'm going to scroll down here, and we'll do a few steps, and then we'll look at the very nice complete solution. Okay, so there's 9 keys in this, so n is 9 in this case, so it's C, D, J, and then R, E, T, and so what you'll do is you'll do this on a sheet of paper, and then take a picture and then just upload it for me to look at. Okay, so your n is 9. There's gonna there's not, well, initially n is 1. Let me just put this. So there's 9 keys. I'll take that back. There are 9 keys, and so your answer will have 9 trees. All you have to do is show the final state. I remember when I used to teach this, I told the students they'd have to show every single exchange. Sometimes there'd be like 3 or 4 exchanges for a key. I'm not sure why I did that. It was just a little crazy. I wanted to see who really loved computer. I think that was it. Who really loves computer science? Okay,
Professor, n n always starts with n plus 1, right?
Well, no, what if every time you add a key, you increase n by 1. So initially, so you put the C initially, so right now we're adding the keys 1 by 1. So we're starting with an empty heap. So initially n is 0, and now we put the C in, right? So now your n is 1. And every time we insert a new key, we increase n by 1. At the end, n will be 9.
Okay.
Does that help, or just let me know if my answer is not clear?
Oh yeah, that was clear.
So 2, we're going to put the D in, and all you're going to do is draw these trees for me. Okay, so C and then the D, right? Because the left, so we always go level by level, right? So first we filled in level 0. Now we're going to fill in level 1. Okay, and then we check, is D greater than C? Is D greater than its parent? And the answer is yes. So we would do an exchange. And now, and also because we added the D, the n would then become 2. So, okay, so we're done with, so that's all you'd have to write for step 2. So let's just do a couple more and then we'll look at the complete solution. Okay, so now we're going to add the J. So it's D, J, no, DC. Your n would now be 3. And see, now you ask yourself, I just inserted the J at position 3, right? We inserted the J at position 3. And because remember, D is at position 1, C is at position 2, J is the first open, 3 is the first open position. And you ask yourself, you compare what's in position 1 and what's in, so J is at position 3, divide 3 by 2, you get 1. So you compare what's in position 1 and 3. And is D, so is that the data at position 1 less than the data at position 3? And it's true. D is less than J. So you would do this exchange here. And the one thing, of course, we know is that at all times, the very top key has to be the biggest value in there. If it's not, because this J here has to be greater than everything. So because otherwise you wouldn't have a max heap. If it was less than some value, something's wrong is going on. Okay, so there now your n is 3. So again, that's all you have to do is the final say. Let's just do one more. Okay, 4. And so 4, okay, so you put that, so the first open, so n is now 4. You put that R at position 4. And this would actually involve, if we're going to show all the exchanges, this would involve 2 exchanges. You'd exchange R and C and then R and J. So you can actually just go directly to the final answer, which is what I'm going to do. Okay, so maybe I won't. First, just this is one more time. I'll just do this. So first you would exchange J. You exchange R. So you put this R in. So you look up at its parent, which is C. C is less than R, so you do this exchange. Okay, but you have to keep looking up. But see, again, the common error would just be, oh, one exchange, let's stop. But you have to keep looking up to, because this is not a max heap. J is less than R. So you compare R and J. R is greater than J. So one more exchange, R, and R becomes the parent of everything. And so that's the last step. And so at that point, yeah, R is at, the array looks something like this. 0 is not filled, so that R is at position 1, and then J, and then D, and then C. And again, there might be more, there's probably more open spaces in the array, because we want to have a bunch of, we're going to add 9 values, so positions 1 through 9 better exist. But if you actually look at the Sedgwick code, he kind of fakes this increasing the size of the array. But yes, and now, and your n would be 4. Okay, so why don't we, any question before we look at the complete answer? And then you'll be doing something like this on the quiz. Most students get this right. If you, I'm not sure why, don't catch on, or maybe don't have a chance to study. I think it's easier than calculus. I think it's way easier than calculus. So, and calculus isn't this fun. So yeah, we don't draw lots of pictures like this. Okay, so there's 9. So you see how the answer is 9 trees. So what is that point? You're only required to show the state of the heap after inserting a key reminder. There are 9 keys, so your answer should contain a sequence of 9 heaps. And so in each heap, and that, so the tree number, like we're going in sequence. So like step 5 would have 5 keys. Step 6 has 6 keys, and you see at every step, like here, like look here at 8. So this is the state of the tree here at 8, and then you're actually going to add the V. You would actually add the V down here. What happens is you exchange V and D, and then V and J, and V and T. So it actually would be 3, you'd actually it would require 3 exchanges at the end. To put the V in its proper place, yeah, it would require 3 exchanges. Right? D and V, and then V and J, and then V and T. So, and the one thing is, you know, when I actually grade these, the one thing I do is I kind of scan it initially, and if I see a heap where one of the parents is less than the child, I mean, I know right away there's a mistake made. Because that's the most common error. That usually happens when people are. See, this requires 3 exchanges. Here's the common error for number 8. Just stop right here. T, J, R, and then you have the D and the B here, and the J, and then this would be V. What I did? I did something wrong here. Let me do it again. This is a common error. The common error would just be to exchange D and V. So this is what I would. Just J, R, and then then V, E, and B, and then so this would be the common error right here. Okay, because we didn't complete, there's still 2 more exchanges. Now you have to exchange V and J. And then you'd have to exchange V and T. So if you can just do that, I think a lot of students can do that in their head, but there's nothing wrong with that's, you know, if writing it all out helps you, and you can either show it to me or just do it in your scrap paper. That's typically one of the things I look at the trees, and I see, is it really a max heap? Do I see anything like, and here I automatically know something is messed up because J is greater than V. And the other common error I see is not adding at the bottom, not going from left to right. See, so the first open position, see here at this point, N is 8, right? So at this point, N is 8. Oh yeah, 8, because there's 8 nodes, 8 trees. So N is 8. So you would actually add at position 9. Well, some students maybe, for whatever reason, they're just heading somewhere else. Maybe they put the V here. So and also, so when you're not, so you're not actually ordering from left to right, I look for that. And the tree is balanced, right? The first open space would be what I'm saying, you're filling in row by row. So you don't see any so it's not ever lopsided on one side. So, any question on anything we've done so far? And so then I have an old quiz for you to look at, to try too. But why don't we just do the second part of this interesting algorithm? And the second part is, well, this would correspond to question 2. So the first thing is, how do we create a MaxPQ just by inserting one by one? Okay, so we've done that. Now the second one, we want to do this problem right here. So it only takes a few slides and so what we're going to do is we're going to pass all these keys at random to the to this MaxPQ program, and we want to create a max heap out of that. So those keys are, and notice that there's some kind of random order. There's nothing special about that. So let me just look at the slides, and though it's really it's not that hard, and it involves something called the opposite of swimming, sinking. We're going to push a key down and put it in its proper place. And so anytime you have to go, I welcome you all to stay, but if, I know it's also getting late for some of you, but this will be taped, but you can always ask questions, but I'll put the tape on tomorrow or maybe tonight. Okay, so we're done with this first algorithm. So we're going to learn, we're going to create a MaxPQ. These slides I think are a little out of order, more I think about it. So first we're going to learn how to sync. And again, students, I'm going to show you the code, but you don't actually need to, it's great to understand the code, but you can do this problem just by drawing. All this is going to be solution by picture. So we're going to learn how to create this maximum heap out of like a series of random nodes, and sort of like a whole array of keys at one time instead of just one by one. And then I'm going to show you how to sort, but we're only going to do one step because it just takes too long to sort. And I don't think this is it's not really considered a very practical sorting method anyway, though it's kind of widely known. Okay, so students, remember, so we're going to sync a key down here. So let's say we have this, we have something like this, let's say C and then P and then Z. And so notice how, so this is a new, so let's say we just have this right here. Well, you can see right away that's not a MaxPQ. C is greater than its two children. So we want to put the C in its proper place. And we're going to do it with something called syncing. We're going to do it with something called syncing. And so in this case, the C is at position 1, K equal to 1. So we're going to sync 1. And so remember, N is the position of the last node. So in this case, N is 3. It's the index of the very last element in the array. And so remember, 2 times K is the position of the left child. So you're going to look at so what we're going to do is first we want to verify that 2 times K is less than or equal to N. Otherwise you're not part of, the index is not part of the max heap anymore. Because remember, N is the greatest index in the array. And you also want to make sure that you get the largest, you're exchanging with the larger of the two children. So like in this example here, you don't want to exchange C and P. You want to make sure you exchange C with the larger of the two children. Right? You want to make sure you exchange with the large, because what happens if you just always exchange with the left? Let's just say arbitrary, let's just exchange with the left. You get P and C, and now, you know what? You're still not a max heap anymore because P is less than Z. So if you start with a tree with just 3 nodes and you exchange the parent with the greater of the two children, you're guaranteed, hello, I don't know why it's not erasing it. You're guaranteed to have a max heap. So ZC, right? Because Z is greater than P, right? So when you move the Z up, it's not going to violate that max heap property. Okay, so we want to make sure that 2 times K is not off, is part of the heap, and then we just say J equal to 2 times K. And now what we're going to do, okay, so if J is less than N, that means that the node has a right child as long as so if J was equal to 2N, then or let's say if 2 times K was equal to N, the node would only have a left child, but not a right child. So if j is strictly less than n, oh, I keep getting these alerts. Sorry, students, I don't know how to turn all these alerts off. I'm not sure how that happened here. Okay, so, okay. Okay, so thank you, Microsoft. Okay, so anyway, so we want to make sure we're choosing the greater of the two children. So that's what this is saying. So if j is less than n, that means that a key. So like here, j would be equal to 2 times 1, which is 2. 2 is less than n, which is 3. So that means that c is a right child, and so that's what this less j comma j plus 1 is. You're trying to find the index of the greater. You're trying to find which children has the greater key. So you're saying, oh, is the key stored at j less than the key stored at j plus 1? And if that's true, you increase j by 1, and you get the right child. That's all this. I'm just, you don't have to know this code. And I remember the first time I looked at it, I had to read that for a while to really kind of understand what's going on. And this is the part that swims down. Okay, so now you're comparing what's in position k with the index of with the position of its greater of its two children. So that's what I'm saying. So if what's in position k, so basically you're just looking at the greater of the two children. C is greater than C. Are you less than the greater of the two children? Which in this case, that's true. C is less than Z. So you would do an exchange. So so let's just see what goes on right here, and then we're going to actually do a complete problem here. So if you look right here, you see here H is greater than S, right? So H is less than its two children, P and S. Okay, so now what we want to do is so that H is at position 2, and the S is at position 5. Okay, so we're going to exchange 2 and 5, and okay, so the first exchange would be, because first it's going to say, well, is P less than S? It is. Okay, so you set J to 5, and now what happens is you exchange H with the greater of its two children. So the first exchange would actually be T and then S, and then the S, you put the H here, and then the P, and then everything else is the same. And then there'd be one more exchange. You compare H with the greater of its two children. In this case, you go to the left. And so first you move H to the right to exchange S, H and S, and then you exchange H and N, and you get this tree right here. So it actually, so to sink H down and put it in its proper place, it would actually require 2 exchanges. So, okay, so now we're going to do, let's actually, I think I need to go down. Yeah, I put these slides are a little bit out of order. We're going to go back to that, how to remove the largest key. It's kind of just following Cedric. I think he does. Sometimes his reading is a little bit hard to do. Okay, so we're going to skip all this. We don't need to know this right now. Okay, so first of all, let's see how we can make, so the first step, let's say you wanted to actually sort, we have this string that's, that sequence of characters, and we wanted to sort that. Okay, so first we actually have to convert into a max heap. So this corresponds to this, there's 2 versions of this max heap algorithm: inserting a key one by one, inserting an array of keys inserting keys one by one, and then the second one is taking an array of keys and converting that into a max heap. So we're going to do a bunch of exchanges. So and basically we're just going to, that's your algorithm right there, and I'll show you. So what you do is you just, so we're going to convert sort example into a max heap. So initially it's not, right? So like the S is at position 1 and the O, so right away, well, actually that is a max heap. S is greater than O and R. So let's see. Oh, then the next one would be T. So so now when you actually look at the first 4, oh, you know what? This should actually, let's notice that should be 1, 2. Okay, whatever. Okay, so I'll make that correction. Okay, but so you look at the first 4. Now you see you're not a max heap anymore. Okay, so you actually have to, so let's actually just do a complete problem here, and then we're going to use this algorithm to do the syncing. Okay, so here's our sequence of characters, and I'll show you what we do here. Sort example. So what we do is we just create this tree-like structure, and we'll just do it with drawings here. So you create that tree-like structure with sort example. The S is at position 1, and then the O is at 2, and the R is at 3, the T is at 4, and so forth. There's 11 keys in here, so this last E would be a position 11, but notice we're going row by row. First, we fill in level 1, then level 0, that's the S, and then the O and the R, and then we go left to right. So the first level is 1, the next 2, the third level, that what I call level 2, has 4, and so forth. And then X doesn't have any children, left to right. Okay, so your N is 11, and what we're going to do is we're going to start by syncing at a position N over 2, which is 5, right? So this algorithm here actually, if you actually do everything in this loop right here, at the end, it's kind of like magic. You will have a max priority queue. So what happens there is that when you start at position N over 2, right, so the 5 here is this E right here. And so notice how it only has 3 keys in there. So you're going to put that E, this E here, position 5, make sure that it's in its proper place. And when you're done, you're going to sync it. And when you're done, you're guaranteed to have a max heap. But there's only 3 keys here. So you're going to take this E and you're going to exchange it with the greater of the 2 children, which is greater, L or E. Well, L is greater than E. So the largest children is L. So you're going to exchange this E and this L. So when you make L the parent, it's guaranteed to be greater than the other child that we didn't exchange it with. So first we're going to create these like these small max priority queues by looking at these subheaps. Oh, let's create, so all these subheaps with size 3, or these subtrees of size 3, we're going to turn into MaxPQs. And then when you put this O in its proper place, you exchange it with the larger of the 2 children, and you're guaranteed to have a MaxPQ. And then actually the proof is by induction, which is kind of beyond the scope of this course. We learn it in math, we learn in Math 265. Okay, so let's look at this first step here. So we're going to start at, remember, we're going to sync, and you're going to start at position 5. So you're going to exchange. So again, there'd be 5. So there's potentially 5 exchanges. So there's going to be 5 trees. And in the end, you'll have a MaxPQ. So the first exchange exchanges this E and this L. And I have a complete example. I think I might only have this first step right here, but we'll look at a worksheet where I have a complete example. So see how we did, we exchanged that E and the L. And now this E, L, L, E, E, that's a MaxPQ. Did I do one more step here? Okay, so, and then we'll look at the sorting in a minute. Okay, so if we're gonna do one more step, okay, so the L is at 5, the T is at 4, so that would be the next step. And it turns out there's nothing to do because T is greater than M and P. So then the next step would be to put this R in its proper place. So it would be S, O, and now you exchange X and R. And I'm not going to write, maybe I will. So T, L, L, E, E. And then we're going to look at a worksheet. And gradually what's happening is you're building up this MaxPQ. So this is a MaxPQ, that's a MaxPQ, this is, and now when you put the O in its proper place, you exchange it. Okay, L is greater than, see this L is greater than E and E, and this T is greater than L. So it's got to be greater than the children of L. So when you exchange O and T, this T will be greater than everything in that right subheap. Okay, so that's basically why this creating this heap from the bottom up works. So why don't we look at a worksheet problem, and then I'll show you the first step of the sorting algorithm. Again, Philip, if anytime, I'm going to record this whole thing, so anytime you have to go, that's fine. I mean, it's great if you can stay, but if you can't, I certainly understand. Okay, so so we're going to do step 2 here. And this basically, this is all we have to do. You just draw the tree, and then you just sync. You start at position N over 2, until you sync what's at position N over 2, and then you just decrease the K by 1 until you sync what's at position 1. And in the end, we better have it, the MaxPQ, the very top node, better be the greatest value. So when we're done, we know that T has to be at position 1. I can't make any claims about the other nodes, but that absolutely has to be at position 1. Okay, so let's look at the first couple of steps, and then we'll look at the solution. Okay, so C, D, I might have had, okay, so let's. Okay, so the first, this is that problem 2. And so what we're going to do again is that very same array, and okay, so there's 9 keys in there. So so remember this, so what we did before is insert keys one by one, and now we're inserting we're passing 9 keys at the same time. So the first thing we do is we just draw this. It looks like that heap, it's that same binary tree, but it doesn't satisfy the binary heap property. But we fill it in. My R's are really bad. Okay, so that's clearly not a max heap, right? C is less than D and J. And D is less than R and E and so forth. Okay, so your N is 9. Your N over 2, our starting place is 4, right? So the first thing that we would sync 4. So step 1, so sync 4, which that corresponds to the R. Okay, so we exchange R with the greater of its 2 children. So we exchange R to the right. So I only do 1 or 2 steps of this, and we'll look at the complete solutions. So there's going to be, we start at position 4, there should be 4 trees. So we're exchanging R and V. So put the V here and the R down here and the D here. And then the left child would be E, and then T and B. And so what we have here, see this bottom part here, that's a MaxPQ. So let's just do one more, and then I have a nicer solution in the solution file. So now we sync 3. So we go sync 4, sync 3, sync 2, and then sync 1. So that's the J. That corresponds to the J. The greater the 2 children is T. So now you'd actually move J to the left. So it'd be C, and then D. So that's a subheap. That's a MaxPQ, and this subtree is a MaxPQ. And then the next step then would be to sync 2, which is the D. And of course, you would exchange D. You actually would have to do 2 exchanges for this D right here. And then the C, there would be a bunch of exchanges. Why don't we look at the complete solution? The suspense is killing me here. Okay, so 2. Okay, so remember we draw the initial tree right here. So that's the initial tree. And then we sync 4, right? We sync 4, sync the R, K equal to 4. So that's what we did here. We exchanged the R and the V. And then we sync the 3. We sync J. Let me see if I can make this a little bit smaller. Yeah, so we sync the R. So the next step is, so step 2, sync J at K equal to 3. So we'd actually exchange that J and that T. And that's what we get here. So the next step, sync the D at K equal to 2. And so here, notice, so the next one is, this is the one we're going to put into its proper place in the next step. So you actually have to exchange D and V, right? And then you have to exchange D and R. So in the end, see, that's a subheap, right? See, when you exchange D with the greater of the 2 children, you're exchanging D with the greater of V and E. So when you exchange D and V is guaranteed to be greater than E, right? Because you exchange D with the greater of the 2 children. So you're not, so when you exchange the D and V, you don't have to worry about what's on the right subtree of V. V is greater to be greater than everything on the right subtree. And then the final step, K equal to 1, right? So the next step, the last thing we'd be syncing is C. So again, that takes 3, in this case, 3 exchanges, right? So you would exchange C and V, C and R. Okay, so now what happens? Okay, so eventually, what happens is eventually you get to here. You get, let's see if I can draw this, V, T, J, and then B, and then what was C and V, and then this would be R, E, and see, I'm kind of running out of room, but you have C and then you have the D on the right. Let's see if I can make this a little bit smaller. What happens, the C would be here, and then you have the D on the right and the D on the left. Which one do you exchange with? Well, if they're equal, you always exchange with to the left, right? Because that's what, how do you determine which is the larger of the two children? At one point in the code, it says is less J. So J would be J represents the left child and J plus 1 is the right child. You're asking yourself, what's that position? Is the left child, is the key at the left less than the tree? Let me say it. Is the key at the left child less than the key in the right child? And if it's true, then you just exchange. You would actually set J to the right. But if they're equal, if this is false, then J would actually stay here at the left. J tells you which key you're going to exchange with. You probably may have to go back to that syncing code to really understand what I'm talking about. But yeah, but all I'm saying is that when you look at the two children, the equal, always exchange with the one on the left. So again, you get this tree here. And it's really not too bad, right? So just create the tree and just start syncing at n over 2. So do you have a question, Philip, or?
I was just wondering, can you do this with numbers as well instead of letters?
Absolutely.
Okay.
Anything that allows you to compare. I mean, I can even use person. I mean, I think it'd be silly. I can create a person, let's say the person class implemented comparable. The keys could be person objects. And then
Okay.
I would just use whatever in the compare to method to compare person objects. So as long as you can compare any kind of objects that you can compare, you can use it. Like the string, like the keys could actually be strings, like words, like cat and dog, or
Right.
how do you compare them?
Okay.
Does that help, or?
Yes, it is. Thank you.
So, okay. So, right here. So let's just do one more. I think I'm just going to start right here. Let's do one more problem. Okay. So, and this is, I'm going to tell you how to sort now. So basically, and I'm going to do one step. Okay. So this is the final answer. So remember, so it says draw the max oriented heap after deleting the max key from the max oriented heap in problem 2. So you'll have, so this is basically step 1 of sorting. So when you sort, what we do is we remove the maximum value and we move that. So the maximum value is always at position 1. We're going to exchange what's at position 1 and position n, and then decrease n by 1. So we're always putting the maximum position n, and then we decrease n by 1. So let's see what happens here. Okay, so here we have n is, what is n? It's 9, right? Yeah, n is 9. So what we're gonna do is your n is 9. Your n is 9. So what we're gonna put that v, which is that. So what happens here is, I might have to just. This is what we have right here. So 0 is kept empty. So we have v. Oh, let's see if I can. Let's write this. V RT and then. Sorry. Let me just write this down. So it's V R T D E J B. Yeah. So what would actually be in the array? So after you heapified your array, it would be V R T and then D E J and then B C D. See that D, so this D would actually be at position 9. So it should be, oh, wait a minute, why is that? Oh, that's right. Okay, so what happens there? So your n is 9. So the step 1 would be to exchange. So draw the max oriented heap after deleting the maximum key. So step 1, I just noticed by step 2 is above step 1. It should really be the other way. Replace V at position 1 with the D at position. So you exchange the first and the last, right? So what we would do is, so now the D would go here, and then everything else stays the same, except we put the V. Now, see how the greatest one goes at position 9, and then So this is at position 9, and what you do is you also then, and you set n to 8. You decrease n by 1. It's only this part is considered part of your heap. The v is still in the array, but it's not considered part of the heap. And so here's your drawing. See, this has eight values, and here your n is 8. Right? We deleted the v. You delete the v just by moving. You exchange what's in position 1 and position n. And now we have to, but now, see, it's not a max heap anymore, right? That d is less than r and t. So now we have to sync d, and you keep, right? So we exchange, we keep moving, we keep exchanging d downward with the greater of its two children until we can't sync anymore. So what happens is, okay, so the d is exchanged with r. Okay, so the d would be exchanged with, the d would be exchanged with t, right? Because t is greater than r. And then you would exchange the d and the j. So in the end, so in the end, what you would have is an array that would look like this. So now the t, right? So of those 8 remaining characters, t is the greatest. It was v, now it's t. So you'd have t, r, j, d, e, d, b, and then c. Okay. Oh, I'm sorry. And then the v would be, I'm sorry, that v would be at position 9, but that's not, but only this part right here is considered part of the heap. The v is still in the array. It's just not considered part of the heap. And now, if you wanted to continue the sorting process, what you would do is you would exchange this d and you exchange that t and the c. You just would keep deleting max, right? So now you would, because now n is 8, so you'd exchange what's in position 1 and position n. So now the t would go in position 8, and then you would decrease n by 1 at 7, and then you would have to sync the c down. We're not going to do all that. So we're just going to do one step. All I'm asking you to do is delete the max key. In this case, the max key was v. Delete v from the heap by, you just basically take it out of the heap, and you move this that d, and you just replace the d with the v. The size of the heap is now 8 instead of 9, and then you sync the d down, right? So step 1, replace v at k equal to 1 with the d at k equal to 9, and then sync d at k equal to 1. So I don't think it's too bad. I probably should maybe decrease n by 1. But so Philip, do you have any questions?
No, I don't.
So I have two. So I'm going to post this video, and I have two, and I have so this worksheets, and then you can practice with that quiz as well. And then from 3 years ago, I have to believe it's 3 years ago already. And then and I'll put up those 2 YouTube videos, which are, the YouTube videos don't show how to delete the max heap, but it does show the 2 ways of creating the max heap. So I'm going to actually stop the recording. I'm going to stop sharing.